Consider the following example from physics. If we hang a weight on the end of a spring, it will stretch. And for different weights, the spring will stretch to different lengths. According to Hooke's law, the amount of stretch is proportional to the weight of the load. That is, we have the relationship y is a plus bx, where y is the total length of the spring, a the length under no load, x the weight of the load, and b the so-called force constant of the spring. We would like to find the values of a and b, and you will discover how to do this using data fitting. Suppose you measure the stretch of the spring for 10 different weights, and you also measure the spring without any weight. Be careful. Due to measurement errors, this latter measurement is usually not equal to the constant a. Alright, so you obtained a list of 11 pairs xy. Next, if you substitute for each pair xy the values of x and y in the equation y is a plus bx, then you end up with a system of 11 linear equations in the two unknowns a and b. Due to measurement and round-off errors, this system will almost certainly be inconsistent, so the method of row reduction would not produce a solution of the system. So how do we proceed? Well, if we plot the points, we obtain a graph like this. What we are looking for is the best straight line for these points. For instance, look at these straight lines. Intuitively, you probably consider the red line the best. And this is indeed the case. But how do we determine which line is the best? Well, the criterion we use is the so-called least squares method, which minimizes the squares of the distances between the straight line and the points. In general, the least squares method deals with large systems of linear equations, which are usually inconsistent, but we would like to find a best almost solution anyway. So, let A be an m by n matrix and be a vector in Rm, and consider the system Ax is B, which might or might not be consistent. If the system is inconsistent, then there exist no vectors x such that Ax is B. The best thing we can do then, if we need to find vectors x which are almost as good as a solution, is to find all vectors x for which the distance between Ax and B is as small as possible. This is a very important idea. And here's the formal definition. A least square solution x hat of the system Ax is B is a vector x hat which satisfies the inequality that the distance between A times x hat and B is smaller than or equal to the distance between A times x and B for all x in Rn. The terminology least squares stems from the fact that the distance between two vectors is the square root of a sum of squares. So, how do we find this least square solution? Well, the idea behind the method of least squares is connected to the theory of orthogonal projections. Recall that the system Ax is B is consistent if and only if B lies in the column space of A. Now, suppose B does not lie in the column space of A. We know that the vector in the column space of A, which is nearest to B, must be the orthogonal projection of B onto the column space of A. Let's denote that vector by B hat. A least square solution x hat must have the property that A times x hat is as near as it can get to B. But since A times x hat lies in the column space of A as well, x hat must satisfy A times x hat is equal to B hat. In other words, the set of all least square solutions of the system A times x is equal to B is the set of solutions of the modified system A times x is equal to B hat. Note that the modified system is always consistent because B hat lies in the column space of A. Also note that if the original system A times x is B is consistent, then any least square solution is in fact an exact solution, because in that case the distance between A times x and B can be 0. So, a system A times x is equal to b, which might be inconsistent, is replaced by the system A times x is equal to b hat, which is always consistent. The solutions of the system are denoted by x hat, and they are the so-called least square solutions of the original system. The remaining question is, how do we compute x hat? Well, using the knowledge you have obtained in the previous lectures, you can solve this problem. You could construct an orthogonal basis of the column space of A, and then compute the orthogonal projection b hat of the vector b on the column space of A. Once you've computed b hat, you could of course solve the consistent system A times x is equal to b hat by means of the method of row reduction. However, in class you're going to learn an alternative way to compute the least square solution x hat. This alternative method works a lot quicker because it bypasses the computation of b hat. I hope that by watching this video, you've become curious to find out how you actually compute the least square solutions of a linear system. Once you've mastered this technique, it will be easy for you to apply this to a data fitting problem, such as the one we gave as an example at the beginning of this video. See you in class.